Nobody talks about what is actually out there. Past Mars, past Jupiter, past everything with a name you recognize. The textbooks show you pretty diagrams, clean orbits, neat little planets on a white background. But strip that away, and what you are left with is one of the most hostile, violent, and alien environments that has ever existed. And here is a question. If you had to spend 500 days on Mars with only 3 books, which 3 would keep you alive mentally? Let me know in the comments. I will pin the most creative answer. Now let's begin. Let's start with something that sounds simple. Mars is the 4th planet from the Sun. You probably learned that in school. It sits roughly 228 million kilometers away from the Sun on average. That's already a staggering distance. Light itself, the fastest thing in the known universe, takes about 12.5 minutes to travel from the Sun to Mars. If you got in a car right now and drove at 100 kilometers per hour without stopping, without sleeping, without eating, it would take you about 260 years to reach Mars. And that's just Mars, the closest neighbor, the one we've been talking about sending humans to for decades. But what lies beyond it? What's on the other side of that rust-colored planet that our telescopes and probes have slowly started to reveal? Well, the first thing you hit, and it's not what most people expect, is not empty space, it's chaos. Right past Mars, starting at roughly 2.2 astronomical units from the Sun, an astronomical unit being the average distance from the Earth to the Sun, about 150 million kilometers, you begin to enter a region that astronomers call the main asteroid belt. And if you've seen movies where spaceships have to frantically dodge giant spinning rocks in some narrow corridor of doom, I have both good news and bad news for you. The good news is that the asteroid belt is not nearly that dense. The average distance between objects in the belt is enormous. NASA's spacecraft have passed through it multiple times without a single collision. Pioneer 10 did it back in 1972, and scientists were genuinely nervous about whether it would survive. It did, barely a scratch, but here's the bad news, and this is where it starts to get real. The asteroid belt contains an estimated 1.1 to 1.9 million asteroids larger than 1 kilometer across. 1 kilometer, that's big enough to end a city if it hit Earth, and beyond those there are millions upon millions of smaller rocks, pebbles, and dust particles swirling in an enormous donut-shaped region around our Sun. The total mass of everything in the belt is less than 4% of the mass of our Moon. It's more emptiness than rock, but that emptiness is not clean. It is cluttered with ancient debris left over from the formation of the solar system roughly 4.5 billion years ago. These are not polished, nicely shaped boulders floating in a neat line. Many of them are jagged, irregular, tumbling through space on orbits that occasionally get nudged by Jupiter's immense gravitational pull. Jupiter is so massive, so incomprehensibly large, that its gravity acts like a cosmic hand, stirring the asteroid belt, pulling objects into new trajectories, occasionally flinging them inward toward the inner planets. Scientists believe Jupiter actually prevented the asteroid belt from ever forming into a proper planet. There was enough raw material there to build a world, but Jupiter kept disrupting the process, scattering the pieces before they could come together. In a very real sense, Jupiter is the reason why there is no 5th rocky planet in our solar system. And speaking of Jupiter, that is where things get truly, genuinely terrifying, because once you cross the asteroid belt, you arrive at the doorstep of a world that operates on a completely different scale than anything in the inner solar system. Jupiter is not just big, it is not just a large planet, it is a monster, a gas giant so enormous that all the other planets in our solar system could fit inside it with room to spare. Its diameter is roughly 140,000 kilometers. Earth's diameter is about 12,700 kilometers. You could line up 11 Earths side by side across Jupiter's face and still have space left over. Its mass is 2.5 times the combined mass of every other planet in the solar system put together, but size is not the most dangerous thing about Jupiter. Not even close. The most dangerous thing, the thing that would kill a human explorer long before they even reach the planet's clouds, is invisible. You cannot see it, you cannot hear it, but it surrounds Jupiter in a vast, churning shell that extends millions of kilometers into space. We are talking about Jupiter's radiation belts. Earth has radiation belts too. You may have heard of them, the Van Allen belts. Discovered in 1958 by Explorer 1, America's first successful satellite. They are dangerous enough that spacecraft have to be shielded when passing through them. But Earth's radiation belts are gentle by comparison. Barely a concern compared to what Jupiter generates. Jupiter's magnetosphere is the largest structure in the entire solar system. If you could see it with your naked eye from Earth, it would appear larger in the sky than the full moon. And Jupiter is hundreds of millions of kilometers away from us. Inside this magnetosphere, charged particles, electrons, protons, heavier ions, get accelerated to enormous velocities and trapped in swirling bands of radiation that would expose a human being to lethal doses in a matter of hours. Not days, not weeks, hours. The Galileo spacecraft, which NASA launched in 1989 and which spent nearly 8 years orbiting Jupiter, was slowly destroyed by this radiation despite being specially shielded. Its electronics degraded over time, instruments malfunctioned. The mission was extraordinary. It gave us our best close-up data of Jupiter and its moons, but the radiation took a real toll on the probe. Eventually, in 2003, NASA deliberately plunged Galileo into Jupiter's atmosphere to prevent it from accidentally contaminating one of Jupiter's moons. It was a death sentence for one of our greatest explorers. And here is what makes this even more remarkable and more haunting. Jupiter's moon Europa, one of the most exciting places in the entire solar system from an astrobiological standpoint, sits right inside the heart of this radiation belt. Europa is a world covered in a shell of ice. Beneath that ice, scientists believe there is a liquid water ocean, a global ocean that may contain more water than all of Earth's oceans combined. And where there is liquid water, there is the possibility of life. Real, actual extraterrestrial life. The Europa Clipper mission, launched by NASA in October of 2024, is on its way there right now. It is one of the most ambitious planetary science missions ever attempted. But designing that spacecraft to survive Jupiter's radiation while still being able to function and send data back to Earth was one of the greatest engineering challenges in the history of space exploration. Think about that for a moment. We have found a place in our own solar system, not light years away, not in some distant galaxy, but right here, around the 5th planet from our Sun, where there might be an ocean teeming with life. And getting there is so difficult, so dangerous, so technically demanding that it has taken us decades of planning and billions of dollars just to send a robot to take a peek. Now imagine what it would take to send a human. But we are just getting started, because beyond Jupiter, beyond the radiation, beyond the asteroid belt, beyond everything we have talked about so far, the solar system gets stranger and quieter and colder and more alien than you can possibly imagine. In the next part of this journey, we are going to leave Jupiter behind and venture into the realm of the ringed giant, Saturn. We will talk about what Cassini found there over its 13 years of exploration and why the space surrounding Saturn holds one of the most beautiful and deadly phenomena in our entire solar system. We will also start to talk about something that scientists only began fully measuring in the last few decades, a force so pervasive, so relentless, and so invisible that it is slowly cooking everything beyond Mars at the atomic level. What is it? You'll find out very soon. And once you know, you'll understand why every mission to the outer planets is essentially a race against time. Welcome back. If you just joined us, we've already crossed the asteroid belt and stared down the terrifying radiation of Jupiter. But we are nowhere near done, not even close, because the deeper we go into this solar system, the more the universe seems to be saying, "You are not supposed to be here. Let's keep moving." Saturn. Just saying the name out loud feels like something out of a dream. It is the sixth planet from the Sun, sitting at an average distance of roughly 1.4 billion kilometers from it. Light from the Sun takes about an hour and 20 minutes to reach Saturn. If you drove there at 100 kilometers per hour, same car, same trip we imagined before, you would arrive in about 1,600 years. That is not a typo. 1,600 years of driving, non-stop, no traffic, no sleep, no stops. And yet, when Voyager 1 and Voyager 2 flew past Saturn in 1980 and 1981 respectively, the images they sent back stopped scientists cold. They were breathtaking. A pale golden giant wrapped in gossamer rings, thin as a piece of paper relative to their width, yet stretching outward for hundreds of thousands of kilometers in every direction. Nothing in the inner solar system prepares you for Saturn. It looks like something an artist invented, like a jewel hanging in the dark. But beauty and danger are two sides of the same coin out here. And Saturn is no exception. The Cassini spacecraft, a joint mission between NASA, the European Space Agency, and the Italian Space Agency, arrived at Saturn in July of 2004 after a 7-year journey from Earth. What followed was one of the most scientifically productive missions in the entire history of planetary exploration. For 13 years, Cassini orbited Saturn, diving through its rings, studying its moons, probing its atmosphere, and sending back data that is still being analyzed today. Over 2,500 scientists across the world have published research based on Cassini's findings. It reshaped everything we thought we knew about the outer solar system, and what it found was staggering. Let's start with the rings themselves, because this is where most people get surprised. Saturn's rings are not solid. They are not like a disk of plastic or metal spinning around the planet. They are made up of countless individual particles, chunks of ice and rock ranging in size from tiny grains smaller than a grain of sand all the way up to boulders several meters across. Billions upon billions of these particles, all orbiting Saturn at different speeds, depending on how far they are from the planet, constantly colliding, clumping, breaking apart and reforming. The rings are dynamic, alive almost. They have waves and ripples in them, caused by the gravitational influence of Saturn's many moons, a phenomenon called orbital resonance, where moons and ring particles pull on each other in rhythmic, repeating patterns. And here is something that genuinely surprised the scientific community even in recent years. Saturn's rings are young. Astronomically speaking, they are practically newborns. Based on data collected by Cassini during its final orbits, a phase of the mission called the Grand Finale, where the spacecraft dove between the planet and its rings, scientists calculated that the rings are only somewhere between 10 million and 100 million years old. That might sound ancient to you and me, but the solar system is 4.5 billion years old. In cosmic terms, Saturn's rings formed yesterday. When dinosaurs roamed the Earth, Saturn may not have had its iconic rings at all. The rings are also slowly disappearing, being pulled into Saturn by its gravity at a rate that means they could be completely gone within another 100 million years or so. We are living in a rare window of cosmic time where we get to see them at all. Now, here is something that does not get nearly enough attention when people talk about Saturn. Something that Cassini discovered that rewrote the textbooks and opened up a whole new chapter in the search for life beyond Earth. Saturn has a moon called Enceladus. It is small, only about 500 kilometers across, a tiny world you could drive across in about 5 hours. It should be a dead, frozen ball of ice. It should be utterly unremarkable. But Cassini revealed that Enceladus is one of the most geologically active bodies in the entire solar system. At its south pole, there are massive geysers, plumes of water vapor and ice particles erupting from cracks in the ice surface that scientists nicknamed tiger stripes. These plumes shoot material hundreds of kilometers up into space. Cassini actually flew directly through them and tasted them, analyzed their chemistry in real time. What it found inside those plumes was extraordinary. Water, complex organic molecules, the building blocks of life as we know it, molecular hydrogen, which on Earth is produced when hot water reacts with rocks in a process called hydrothermal activity, silica nanoparticles, which form when hot water dissolves rock and then cools. And most recently, researchers analyzing Cassini's data have detected phosphorus, a critical element for life, in the plumes of Enceladus. Phosphorus is a key ingredient in DNA and cell membranes. It is one of the 6 essential elements for life as we know it, and for a long time, scientists were unsure if it existed in Enceladus's ocean. Now we know it does. Beneath those tiger stripe cracks, there is a global liquid water ocean in contact with a rocky seafloor, kept warm by tidal forces, gravitational squeezing from Saturn that generates heat in the Moon's interior. The conditions inside that ocean may be similar to the hydrothermal vents deep in Earth's oceans, where life thrives in total darkness at crushing pressures, in water that would boil your skin off, ecosystems powered not by sunlight, but by the chemical energy of the Earth itself. If life can exist in those extreme environments on Earth, why not inside Enceladus? This is not speculation. This is not science fiction. This is peer-reviewed science, published in journals like Nature and Astrobiology, based on direct measurements taken by a spacecraft we built and launched. We may have already flown through an ocean spray from a world that harbors life. That thought should stop you in your tracks. Before we go further, if this kind of deep dive into the cosmos is the kind of content that makes your brain light up, do me a small favor right now. Hit that subscribe button and leave a like on this video. It genuinely helps more people find these ideas, and building this community one curious mind at a time means everything to me. Every single subscriber is a reminder that there are people out there who want to understand the universe, not just scroll past it now. Back to the journey, because beyond Saturn, the solar system begins to feel genuinely alien. The sun, which at Earth feels like an overwhelming presence, warm on your skin, bright enough to blind you, begins to fade. By the time you reach Saturn, the sun appears only about 1/100th as bright as it does from Earth. It is still the dominant light source, but it looks more like a very bright star than the massive blazing furnace we know it as. The warmth you feel on a summer afternoon, that is gone. Saturn's average temperature hovers around -178 degrees Celsius. That is cold enough to freeze most gases, cold enough to make our worst winters seem tropical, but it gets colder, much, much colder. Beyond Saturn lies Uranus, the 7th planet, the ice giant that rotates on its side, literally tilted at about 98 degrees relative to its orbit, meaning it essentially rolls around the sun like a bowling ball instead of spinning upright like the other planets. Scientists believe this bizarre tilt was caused by a massive collision early in the solar system's history. Something roughly the size of Earth smashed into Uranus billions of years ago and knocked it sideways. The effects of that ancient catastrophe are still visible today. Uranus sits at an average distance of about 2.9 billion kilometers from the Sun. Sunlight takes roughly 2 hours and 40 minutes to reach it. Its average temperature is around -220 degrees Celsius, making it the coldest planetary atmosphere in the solar system, even colder than Neptune, which is farther from the Sun. Scientists are still not entirely sure why. There may be some internal process, or lack of one, that prevents Uranus from radiating heat outward the way the other giant planets do. It is one of the lingering mysteries of our solar system. And then there is Neptune, the eighth and final planet, a deep electric blue world sitting at an average of roughly 4.5 billion kilometers from the Sun. Sunlight takes over 4 hours to travel there. Neptune was discovered in 1846, not by observation but by mathematics. Scientists noticed that Uranus was not moving exactly the way their gravitational models predicted it should. Something was pulling on it, tugging at its orbit, and by calculating where that gravitational influence was coming from, they were able to predict, before anyone had ever seen it, exactly where a new planet should be. When astronomers pointed their telescopes at that precise location in the sky, there was Neptune. It was one of the greatest triumphs of mathematics and scientific reasoning in human history. Neptune's winds are the fastest in the solar system. We are talking about wind speeds of up to 2,100 kilometers per hour, faster than the speed of sound on Earth. Storms the size of entire planets churn through its atmosphere. The Great Dark Spot observed by Voyager 2 during its flyby in 1989 was a storm system roughly the size of Earth itself. It later disappeared and reformed in a different location. Neptune's atmosphere is dynamic, turbulent, and relentless in a way that makes our most violent hurricanes look like a light breeze. And Voyager 2 is the only spacecraft that has ever visited Neptune, just one. A single flyby in 1989, lasting a matter of hours, from which we gathered most of our close-up data on the planet. Everything else we know about Neptune comes from telescopes, including the Hubble Space Telescope and more recently the James Webb Space Telescope, which in 2022 captured stunning new images of Neptune's rings in infrared light, revealing details and structures we had never seen before. We have sent one spacecraft past Neptune. Think about that. We live in a civilization that can stream video in real time from the other side of the world, that has put rovers on Mars and robots in the deepest trenches of the ocean, that has sequenced the human genome and detected gravitational waves from colliding black holes billions of light years away. And yet the eighth planet in our own solar system has been visited by exactly one spacecraft for a few hours. Nearly 40 years ago, the outer solar system is not just distant. It is unexplored in a way that should humble every single one of us, but even Neptune is not the end, not even close, because beyond Neptune begins a region of the solar system so vast, so strange, so filled with icy wanderers and ancient relics of the solar system's birth, that it challenges our very definition of where the solar system ends and interstellar space begins. We have left the planets behind, all 8 of them. The last one, Neptune, that distant blue world of supersonic winds and ancient mysteries, is now behind us. And if you were sitting in a spacecraft at this point in the journey, looking back toward the sun, you would see something that would hit you like a punch to the chest. The sun, our sun, the star that gave birth to every living thing on this planet, the furnace that drives our weather, our seasons, our entire existence, would look like nothing more than a very bright star. Brilliant, yes, unmistakably the brightest point of light in the sky, but just a point, just a dot of light in an ocean of darkness. Welcome to the outer edge of the known solar system. Welcome to the Kuiper Belt. The Kuiper Belt begins at roughly 30 astronomical units from the Sun, that is 30 times the distance from Earth to the Sun, and extends outward to about 50 astronomical units. In raw kilometers, we are talking about a region that stretches from roughly 4.5 billion to 7.5 billion kilometers from the Sun. It is an enormous, donut-shaped region of space, somewhat similar in structure to the asteroid belt we crossed much earlier in our journey, but vastly larger. If you could somehow shrink the asteroid belt down and place it next to the Kuiper Belt, the Kuiper Belt would dwarf it completely. It is estimated to be roughly 20 times as wide and anywhere from 20 to 200 times as massive. But here is what makes the Kuiper Belt genuinely fascinating and strange. It is not just a debris field, it is a fossil, a frozen archive of the solar system's earliest history. The objects out here, called Kuiper Belt objects or KBOs, are made primarily of frozen volatiles. That is the scientific term for things like water ice, ammonia and methane, all frozen solid at temperatures hovering around -220 degrees Celsius. These are not the rocky metallite asteroids of the inner belt. These are ancient, primordial icebergs drifting in the dark, largely unchanged since the solar system formed 4.5 billion years ago. Studying them is like reading pages from a book written at the very dawn of our cosmic neighborhood. And the most famous resident of the Kuiper Belt, the one that changed everything we thought we knew, the one that sparked a fierce international debate and ultimately lost its status as a planet, is Pluto. Now, before you feel too sorry for Pluto, let me tell you what we actually know about it. Because the story of Pluto is not a sad story of demotion. It is an extraordinary story of discovery. Pluto was found in 1930 by a young astronomer named Clyde Tombaugh at the Lowell Observatory in Arizona. He was 24 years old, manually comparing photographic plates of the night sky, looking for a point of light that moved slightly from one image to the next, the telltale sign of a nearby object in our solar system. He found it, and for 76 years, Pluto was called the ninth planet. Then, in 2006, the International Astronomical Union formally redefined what it means to be a planet. The new definition required a celestial body to, among other things, have cleared the neighborhood around its orbit of other debris. Pluto, sitting in the heart of the Kuiper Belt, surrounded by thousands of similar icy objects, had clearly not done that, so it was reclassified as a dwarf planet, a decision that sparked outrage among the public, heated debate among scientists, and a cultural moment that people still talk about today. But here is the thing: the reclassification did not make Pluto less interesting. If anything, it made it more interesting. Because what New Horizons revealed when it finally arrived there changed the scientific community's understanding of what a small, distant, frozen world can be. New Horizons was launched in January of 2006, the same year Pluto lost its planetary status, as if the universe had a sense of irony. It was the fastest spacecraft ever launched at that time, leaving Earth at a speed of about 58,000 kilometers per hour. And yet, even at that incredible velocity, it took 9.5 years to reach Pluto. 9.5 years of traveling at speeds that would take you from New York to Los Angeles in about 4 minutes. And it still took nearly a decade to get there. On July 14, 2015, New Horizons made its closest approach to Pluto. The images it sent back were jaw-dropping. Scientists expected a dead, cratered, geologically inert ball of ice. What they got instead was a world of astonishing complexity. Towering mountains of water ice reaching 3,500 meters high, comparable to the Rocky Mountains on Earth. Vast nitrogen ice plains that scientists named Tombaugh-Regio, a heart-shaped region so prominent it was visible from space, and named in honor of the man who discovered Pluto. Possible evidence of ancient liquid water beneath the surface. An atmosphere, thin yes, but real, composed mostly of nitrogen with traces of methane and carbon monoxide, that creates a faint blue haze visible in images taken when New Horizons looked back at Pluto with the sun behind it. Pluto is not a dead world. It is geologically active in ways that scientists are still trying to fully explain. There are regions on its surface that are almost entirely free of impact craters, which in planetary science means they are young, geologically speaking. Something is resurfacing parts of Pluto, erasing the old scars and laying down fresh terrain. Whether this is driven by internal heat, by convection in the nitrogen ice, or by some other process is still being actively debated. Pluto keeps surprising us, and Pluto is not alone, not even close. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across. We have catalogued thousands of them and suspect hundreds of thousands more remain undiscovered. Some of the more notable ones have names you might recognize. Eris, a dwarf planet slightly smaller in volume than Pluto, but actually more massive, discovered in 2005, whose existence triggered the whole planetary reclassification debate in the first place. Makemake, Haumea, an oddly elongated world that rotates so fast it has flattened into an egg shape, completing one full rotation in about 3.9 hours. Sedna, a mysterious pinkish-red object on an extraordinarily elongated orbit that takes it as far as 937 astronomical units from the Sun at its most distant point. Sedna is so far out, and its orbit is so strange, that some scientists believe it may have been gravitationally influenced by another star that passed close to our solar system billions of years ago, or possibly by a yet undiscovered large planet lurking in the outer darkness. That last idea brings us to something that has been causing serious excitement and serious controversy in the astronomical community for about a decade. The idea of Planet 9 in 2016, astronomers Konstantin Batygin and Mike Brown at the California Institute of Technology published a paper arguing that the unusual clustering of orbits among several distant Kuiper Belt objects could be explained by the gravitational influence of a large, undiscovered planet lurking far beyond the known solar system, not a small dwarf planet, a real, substantial world, potentially 5 to 10 times the mass of Earth, orbiting the Sun at distances of perhaps 400 to 800 astronomical units on a highly elongated path that brings it no closer than about 300 astronomical units even at its nearest point. If Planet 9 exists, and that is still a very significant if, it would be so far from the Sun that sunlight would take over 40 hours to reach it. It would be so cold, so dark, and so distant that even our best telescopes have not been able to find it directly. We are inferring its existence from the gravitational shadows it casts on smaller objects. The same way Neptune was found in the 1800s, not everyone is convinced. Some scientists argue that the clustering of orbits that Batygin and Brown observed is a statistical artifact, a result of observational bias, meaning we tend to discover objects in certain parts of the sky more than others, which makes clusters appear where none truly exist. The debate is ongoing, the search continues, and the answer, when it finally comes, will reshape our understanding of the solar system's structure and history. But here is something even more profound to sit with. Even if Planet 9 does not exist, even if the Kuiper Belt is the last true outpost of significant planetary bodies in our solar system, we are still nowhere near the edge of the Sun's influence. Not even remotely close, because beyond the Kuiper Belt, beyond even the most distant reaches of what we typically think of as the solar system, there exists a structure so vast, so ancient, and so poorly understood that astronomers have spent decades debating whether we will ever be able to directly observe it. It has been theorized since the 1950s. Its existence has been inferred from the behavior of long-period comets, those icy wanderers that sweep through the inner solar system once every thousands or even millions of years on elongated orbits that carry them from the deep outer darkness all the way in past Earth and back again. And its name, when you say it out loud, sounds almost mythological, the Oort cloud. We are going to spend a lot of time on this in the next part of our journey, because the Oort cloud forces us to completely reconsider the scale of space, what you know, what you think you understand about distances in the solar system. is about to become completely inadequate, because the Oort cloud does not extend to a few billion kilometers from the Sun. It does not extend to tens of billions. It extends, according to current scientific models, to somewhere between 2,000 and 100,000 astronomical units from the Sun. In kilometers, the outer edge of the Oort cloud may be as far as 15 trillion kilometers away, 15 trillion, and light, moving at roughly 300,000 kilometers per second, would take over a year to travel from the Sun to the outer edge of the Oort cloud. Let that number breathe for a second. Our solar system, if you include the Oort cloud, may extend over 1 light-year from the Sun in every direction, possibly further, and we have never sent a single spacecraft there, not one. The fastest objects humanity has ever launched, the Voyager probes, will not reach even the inner edge of the Oort cloud for another 300 years. At current speeds, it would take them about 30,000 years to reach the outer boundary. 30,000 years. We are, in the most humbling possible sense, just barely beginning to understand the place we live in. There is a moment that happens to almost everyone who seriously studies astronomy. A moment where the numbers stop being numbers and start being something else entirely. Something that lands in your chest rather than your brain. A kind of vertigo, not from height, but from scale. From the sudden, visceral realization that the universe is not just big in the way that a mountain is big, or an ocean is big, or even a continent is big. It is big in a way that has no human reference point, no comparison that truly works, no analogy that does not eventually break down. We are about to have that moment together because we are now going to talk about the Oort cloud. And the Oort cloud is where human intuition about distance completely falls apart. Let's back up for just a second and make sure we are standing on solid ground before we take this leap. You know what a kilometer is. You have driven them, run them, maybe cycled them. 1 astronomical unit, the average distance from Earth to the Sun, is about 150 million kilometers. We have established that. Neptune, the farthest planet, sits at about 30 astronomical units from the Sun. The Kuiper Belt extends out to roughly 50 astronomical units. These are large numbers, yes, but they are numbers your brain can at least attempt to process. Now here is where it gets hard. The Oort cloud is theorized to begin at roughly 2,000 astronomical units from the Sun. Its inner edge, the closest part of it to us, is already 40 times farther from the Sun than Neptune, 40 times. And its outer edge? Current models suggest it extends somewhere between 40,000 and 100,000 astronomical units out. Some estimates push even further. Let's use the middle of that range, about 50,000 astronomical units, and do something that I think will genuinely shake you. 1 astronomical unit is 150 million kilometers. Multiply that by 50,000. The outer edge of the Oort cloud sits roughly 7.5 trillion kilometers from the Sun. 7.5 trillion. If you wrote that number out, it would be a 7 followed by 12 zeros, and light, which travels at nearly 300,000 kilometers every single second, which means it could circle the entire Earth 7.5 times in 1 second, takes roughly 8 months to travel from the Sun to the outer edge of the Oort cloud. Now let's put that in a different frame. The nearest star to our Sun is Proxima Centauri, sitting at about 4.2 light-years away. 1 light-year is roughly 9.5 trillion kilometers. So the outer Oort cloud, at its most distant theoretical boundary, extends nearly 1 light-year from the Sun, which means our solar system, if you define its edge as the boundary of the Sun's gravitational influence, reaches almost a quarter of the way to the nearest star. We do not live in a tidy little pocket of the galaxy. We live in an enormous, sprawling, loosely bounded sphere of gravitational influence that bleeds almost imperceptibly into interstellar space. Now, who theorized all of this? Because no human being has ever seen the Oort cloud directly, no telescope has imaged it, no spacecraft has visited it. It exists in a very real sense as an inference. A ghost, we know, is there because of the trails it leaves behind. The man who first proposed the existence of this structure was a Dutch astronomer named Jan Oort. In 1950, he published a landmark paper in which he analyzed the orbital characteristics of long-period comets, those icy travelers that occasionally sweep through the inner solar system on orbits that take hundreds, thousands, or even millions of years to complete. He noticed something striking. The orbits of these comets, when traced backward mathematically, seem to originate from a vast, roughly spherical region surrounding the solar system at enormous distances, not from a flat disk like the Kuiper Belt, but from a sphere, coming at the inner solar system from every direction, every angle, every point of the compass. North, south, east, west. Long-period comets arrive from all directions equally. This told Oort something profound. Whatever was sending these comets inward was not a flat disk aligned with the plane of the solar system. It was a shell, a roughly spherical cloud of icy bodies surrounding the solar system on all sides, occasionally disturbed by gravitational nudges from passing stars, the gravitational tide of the Milky Way galaxy itself, or rare encounters with giant molecular clouds, vast regions of gas and dust drifting through our galaxy. Any of these disturbances can perturb an Oort cloud object enough to send it falling inward toward the Sun on a long looping orbit, and after a journey of perhaps millions of years through the darkness, that object arrives in the inner solar system as a comet, growing a tail of gas and dust as the Sun's heat vaporizes its surface, blazing briefly across our sky before retreating back into the dark. Every great comet you have ever heard of, every icy visitor that has graced our skies throughout human history, likely originated in the Oort cloud. Comet Hale-Bopp, which dazzled observers worldwide in 1997, is believed to have originated there. Its orbital period, the time it takes to complete one full loop around the Sun, is estimated at roughly 2,500 years, meaning the last time it visited the inner solar system, human civilization was just beginning to develop writing. Comet Halley, perhaps the most famous comet of all, is actually a short-period comet that likely originated in the Kuiper Belt rather than the Oort cloud, but it illustrates the point beautifully. These ancient wanderers carry within their frozen cores the raw chemical material from which the solar system was built. Some scientists have proposed that comets may have played a crucial role in the origin of life on Earth. The idea, called panspermia in its broader form, or more specifically the concept of cometary delivery, suggests that the water in Earth's oceans and possibly some of the organic molecules necessary for life may have been delivered to the early Earth by comets and asteroids during a period of intense bombardment roughly 4 billion years ago, called the Late Heavy Bombardment. If this is true, and it remains an active area of research, then the icy wanderers of the Oort cloud are not just relics of our solar system's birth. They may be the reason you exist, the reason any life on Earth exists at all. But the Oort cloud holds another secret, one that brings us to a topic that most people never consider when they think about space. And that is the question of what actually lives in the vast emptiness between the Oort cloud and the nearest star. What is interstellar space actually made of? Because most people imagine it as pure, absolute nothing. A perfect vacuum, the most complete emptiness possible, and that picture is wrong. Interstellar space is not empty. It is filled, thinly but genuinely filled, with what astronomers call the interstellar medium. This is a diffuse mixture of gas and dust that permeates the space between stars throughout the entire galaxy. The interstellar medium has several distinct components. The coldest and densest regions are called molecular clouds. Vast, dark structures made primarily of molecular hydrogen along with traces of other molecules including water, carbon monoxide, ammonia, and remarkably, complex organic molecules. Over 300 different molecules have been detected in the interstellar medium, including amino acids, the building blocks of proteins, and sugar molecules. The raw ingredients for life are not confined to planets. They are scattered throughout the galaxy, drifting between the stars in the cold dark between worlds. The average density of the interstellar medium is extraordinarily low by any earthly standard, roughly 1 atom per cubic centimeter in typical regions. For comparison, the air you are breathing right now contains about 2.7 times 10 to the 19th power molecules per cubic centimeter. That is 27 million trillion molecules in every cubic centimeter of air. Interstellar space contains just one atom on average in a volume the size of a sugar cube, and yet that thinness adds up over interstellar distances. A spacecraft traveling from our solar system to Proxima Centauri, a journey of 4.2 light-years, would pass through an almost unimaginable volume of space, and over those distances, even the sparse interstellar medium becomes meaningful. It creates a faint drag, it carries radiation, it is not nothing, it never was. There is also something else traveling through interstellar space that is far more energetic and far more dangerous than a few stray hydrogen atoms. Something that has no mass, travels at the speed of light, and passes through solid matter as though it barely exists. Something that right now, at this very moment as you watch this video, is passing through your body, through your brain, through every cell of your being. Cosmic rays. Cosmic rays are not actually rays in the traditional sense. They are high-energy particles, primarily protons, but also heavier atomic nuclei that travel through space at velocities approaching the speed of light. Some of them carry energies so extreme that they dwarf anything produced by the most powerful particle accelerators human beings have ever built. They come from all directions. They come from supernovae, the explosive deaths of massive stars. They come from pulsars and neutron stars. They come from the jets of supermassive black holes at the cores of distant galaxies. Some of the most energetic ones, called ultra-high energy cosmic rays, have energies so enormous that their origin is still not fully understood. On Earth, we are largely protected from cosmic rays by two things: our planet's magnetic field and our atmosphere. The magnetic field deflects many of the lower energy particles. The atmosphere absorbs much of the rest, triggering cascades of secondary particles that largely dissipate before reaching the ground. Some do make it through, and they have real effects. Cosmic rays are one of the reasons why airline pilots and frequent flyers accumulate a slightly higher radiation dose than people who spend their lives at sea level. They are also one of the drivers of genetic mutation over evolutionary timescales, contributing in a very small way to the diversity of life on Earth. But in space, beyond the protective cocoon of Earth's magnetic field and atmosphere, cosmic rays are a serious and largely unsolved problem for human exploration. On a mission to Mars, which would take roughly 6 to 9 months one way with current technology, astronauts would be exposed to radiation doses far exceeding what is considered safe by any regulatory standard on Earth. Studies based on data from the Curiosity rover's radiation assessment detector, which measured radiation levels during its cruise to Mars and on the Martian surface, suggests that a round trip to Mars would expose astronauts to a cumulative radiation dose high enough to meaningfully increase their lifetime risk of cancer. And Mars is our nearest neighbor, the most accessible destination beyond Earth, beyond Mars, beyond Jupiter, out in the deep outer solar system and into interstellar space. The radiation environment becomes even more extreme. The heliosphere, the vast bubble of solar wind that our sun inflates around itself, extending outward past the planets and into the outer solar system, provides some shielding from the most energetic galactic cosmic rays. But this protection weakens with distance from the Sun. And outside the heliosphere, in true interstellar space, there is no solar wind shielding at all, just the bare radiation of the galaxy, unfiltered and relentless. The Voyager spacecraft, our only emissaries to interstellar space, have been measuring this transition region since the early 2000s. Voyager 1 crossed the boundary of the heliosphere, called the heliopause, in August of 2012. Voyager 2 crossed it in November of 2018. Both probes detected a sharp increase in galactic cosmic ray intensity as they moved beyond the heliopause, a direct measurement of the radiation environment that any human traveler to interstellar space would have to survive. We do not yet have the technology to protect human beings adequately for interstellar travel, not even close. The shielding required to block the most energetic cosmic rays would be so heavy that it would be essentially impossible to launch with any near-future rocket technology. This is not a minor engineering challenge. It is a fundamental physical problem that will require genuinely new solutions, new materials, new technologies, possibly even new physics, to overcome, and yet, we have crossed the heliopause. We have sent 2 small gold-plated ambassadors from Earth into the space between the stars. Voyager 1 is currently over 23 billion kilometers from the Sun, the farthest any human-made object has ever traveled. It is moving away from us at roughly 61,000 kilometers per hour, and it is still sending us data. Faint whispers from the edge of the unknown, received by enormous dish antennas on Earth, traveling for over 22 hours at the speed of light before they arrive. Voyager 1 was launched in 1977. It carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, a greeting from humanity to whoever or whatever might someday find it drifting through the galaxy. Music, greetings in 55 languages, the sound of rain, surf, wind and thunder, a mother's first words to a newborn child, Beethoven, Chuck Berry, a Navajo night chant. It has been traveling for nearly 50 years, and it has covered less than 1 light day of distance. The nearest star is 4.2 light-years away. At Voyager 1's current speed, it would take roughly 73,000 years to reach Proxima Centauri. If it were even heading in that direction, which it is not, the stars are not just far away. They are so far away that our fastest spacecraft, launched nearly half a century ago, would need more time than human civilization has existed to reach even the closest one. That distance, that silence, that yawning, incomprehensible gulf between the stars. That is what we are going to begin confronting in Part 5. Because interstellar space is not just empty and irradiated, it is home to phenomena so violent, so energetic, so cosmically extreme that entire stars are destroyed by them. Phenomena that release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. We are going to talk about supernovae, about neutron stars and pulsars, about the most extreme objects in the known universe. And we are going to ask a question that scientists have been wrestling with for decades. How close does one of these cosmic catastrophes have to be to end all life on Earth? Because the answer, it turns out, is closer than most people are comfortable with. And if you are still here with me, still traveling through this cosmic nightmare, make sure to hit that subscribe button and drop a like on this video. It genuinely helps more people find this content, and honestly, knowing that curious minds like yours are on this journey with me makes all the difference. Now let's keep going. Let me ask you something. When you think about the end of the world, really think about it, what do you picture? An asteroid impact maybe, a runaway climate catastrophe, a pandemic, nuclear war. These are the threats that fill news cycles, that drive policy debates, that keep scientists and governments up at night. They are real, they deserve attention, But there is another category of existential threat that almost never makes the headlines. One that comes not from within our civilization, not even from within our solar system, but from the galaxy itself. From the violent, spectacular deaths of stars so massive they make our sun look like a candle next to a bonfire. We are talking about supernovae, and once you understand what they are, how powerful they are, and how close they have come to terrorizing our planet in the past, you will never look at the night sky with quite the same sense of peace again. Let's start with the basics. Because the physics of a supernova is one of the most extraordinary stories in all of science, most stars, including our sun, will die relatively quietly. When our sun exhausts its hydrogen fuel in roughly 5 billion years, it will swell into a red giant, expanding outward to perhaps 100 times its current diameter, likely engulfing Mercury, Venus, and possibly Earth in the process. Then it will shed its outer layers into space, creating a beautiful glowing shell of gas called a planetary nebula, while the core collapses into a dense, slowly cooling ember called a white dwarf. It is a gentle death by cosmic standards, dignified almost. But stars that are significantly more massive than our sun, roughly 8 times more massive or greater, die very differently. They die violently, cataclysmically. In one of the most energetic events the universe is capable of producing, here is how it works. A massive star spends its life burning through progressively heavier elements in its core. It starts with hydrogen, fusing it into helium. When the hydrogen runs out, it begins fusing helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. And here is where the story takes a dark turn. Iron is the end of the line. Iron cannot be fused to release energy. Fusing iron actually requires energy rather than releasing it. So when a massive star builds up an iron core, the fuel runs out instantaneously on cosmic timescales. In a fraction of a second, literally less than a second, the iron core, which may be roughly 1.5 times the mass of our sun, compressed into a sphere about the size of Earth, collapses catastrophically under its own gravity. It implodes. The core shrinks from roughly 10,000 kilometers across to roughly 30 kilometers across in about a quarter of a second. That is not a typo. The core of a star, in less time than it takes you to blink, collapses from a sphere the size of Earth to a sphere about the size of a city. The outer layers of the star, still falling inward, hit this suddenly rigid, incredibly dense, collapsed core and bounce. The resulting shockwave tears the entire star apart in a colossal explosion, a core collapse supernova. And the energy released in this event is almost beyond comprehension. In the first 10 seconds of a core collapse supernova, more energy is released than our sun will produce over its entire 10 billion year lifetime. Not 10 times more, not 100 times more. More, full stop. The sun's entire lifetime of energy production, in 10 seconds, 99% of that energy comes out not as light or heat, but as neutrinos, ghostly, nearly massless particles that interact so weakly with matter that they pass through the entire Earth as though it were not there. The remaining 1%, still an almost unimaginable amount of energy, comes out as light, heat, and the kinetic energy of expanding material. A supernova at its peak brightness can outshine an entire galaxy. A single exploding star, briefly radiating more light than 100 billion suns combined. We have observed supernovae in distant galaxies through telescopes. We have watched stars vanish and be replaced by brilliant new points of light. We have detected the neutrinos from a supernova, most famously from supernova 1987A, an explosion in the Large Magellanic Cloud, a dwarf galaxy neighboring our own Milky Way, located about 168,000 light-years away. On February 23, 1987, neutrino detectors buried deep underground on 3 continents simultaneously registered a burst of 24 neutrinos arriving from that direction, a neutrino flood so intense that detectors designed to catch maybe 1 or 2 neutrinos per day were overwhelmed in a matter of seconds. Those neutrinos had traveled for 168,000 years through the void of intergalactic space, and they arrived at Earth several hours before the light from the explosion, because the neutrinos were produced in the very first moments of the collapse and escaped immediately, while the light had to fight its way through the dense outer layers of the star before breaking free. Supernova 1987A was the closest observed supernova since Johannes Kepler observed one in our own galaxy in 1604, and it was 168,000 light-years away. Safe, comfortably beyond any range where it could cause us harm. We watched it through telescopes, measured it with detectors, published thousands of scientific papers about it, and no one lost any sleep about personal safety. But here is the question that keeps some astronomers genuinely uneasy at night. How close does a supernova have to be to actually threaten life on Earth? The answer that has emerged from decades of research is somewhere in the range of 25 to 50 light-years. Within that distance, a core collapse supernova would bathe our planet in a lethal flood of gamma rays, X-rays, and high-energy particles intense enough to strip away significant portions of our ozone layer. The ozone layer, that thin shield of molecules roughly 15 to 35 kilometers above Earth's surface, is what protects all life on land from the sun's ultraviolet radiation. Damage it severely enough, reduce it by 50% or more, and ultraviolet levels at Earth's surface would rise to levels lethal to most complex life. Food chains would collapse, ecosystems would unravel, extinction on a massive scale would follow, and here is the part that should really make you stop and think. There is growing scientific evidence that this has actually happened, that a nearby supernova, or possibly a series of them, may have triggered one of Earth's mass extinction events. The evidence comes from an unexpected place, the ocean floor, specifically from deep-sea sediment cores that contain traces of an isotope called iron-60. Iron-60 is a radioactive isotope produced in supernova explosions. It does not occur naturally on Earth in significant quantities. Any iron-60 that existed when Earth formed would have long since decayed away, given its half-life of about 2.6 million years. So when scientists find elevated concentrations of iron-60 in deep-sea sediment layers, it means that material from a supernova explosion arrived at Earth and was deposited in those layers at that specific time in history. Multiple research teams have found exactly this. Elevated iron-60 concentrations in ocean sediments corresponding to several different time periods, most notably around 2 to 3 million years ago, which corresponds to a period of significant climate change and biological turnover that some researchers have connected to nearby stellar explosions. The local bubble, the region of relatively low-density interstellar space that our solar system currently sits inside, is believed to have been carved out by a series of supernovae over the last several million years. We are living inside the remnant cavity blown out by exploding stars, but let's bring this closer to home, literally closer, because one of the most discussed potential supernova threats in popular astronomy involves a star you have probably heard of, a star visible to the naked eye, a star that has been behaving strangely, inexplicably, in ways that have captured the attention of professional and amateur astronomers worldwide. Betelgeuse. Betelgeuse is a red supergiant star, one of the largest and most luminous stars visible to the naked eye, sitting in the constellation Orion. It marks Orion's right shoulder in the familiar pattern of that constellation. It is massive, staggeringly massive. If you placed Betelgeuse at the center of our solar system, its outer atmosphere would extend past the orbit of Jupiter. It is roughly 700 times the diameter of our Sun, and it is close, astronomically speaking. Current estimates place it at roughly 550 light-years from Earth, though this measurement carries some uncertainty. Betelgeuse is a star in the late stages of its life. It has already burned through most of its hydrogen and helium and is now fusing heavier elements in its core. It will explode as a supernova, eventually. Astronomers are confident of this. The question is not whether, but when, and on cosmic timescales, that means somewhere between now and roughly 100,000 years from now. It could happen tonight. It could happen in 100,000 years. We genuinely do not know. What we do know is that when Betelgeuse explodes, it will be spectacular. From Earth, it will appear roughly as bright as a quarter moon, visible in broad daylight for weeks or possibly months. It will be one of the most dramatic astronomical events in recorded human history, and at 550 light-years, it is well outside the danger zone. It will not harm us. It will be beautiful. A reminder written in light of the universe's power and indifference. But in late 2019, something happened to Betelgeuse that genuinely startled the astronomical community. The star, which normally ranks among the top 10 brightest stars in our night sky, began to dramatically dim. Between October of 2019 and February of 2020, Betelgeuse lost roughly 2/3 of its typical brightness, dropping from around the 7th brightest star in the sky to around the 21st. This event, which astronomers quickly named the Great Dimming, triggered a flood of observations, analysis, and no small amount of excited speculation. Was this it? Was Betelgeuse about to go supernova? The answer, as determined by a wealth of subsequent research, was no, at least not yet. The most widely accepted explanation for the Great Dimming is that Betelgeuse ejected a massive plume of gas and dust from its surface, and as that material cooled and condensed into dust particles, it temporarily blocked some of the star's light from reaching us. A stellar sneeze, essentially a convective mass ejection on a scale our Sun could never produce. The dust gradually dispersed, and Betelgeuse returned to near-normal brightness. But the episode was a reminder that massive stars in their final stages of life are not stable, predictable objects. They are dynamic, churning, unstable furnaces that can change dramatically on timescales of months to years, and one day, without warning, one of them close enough to find with the naked eye will explode. Now, if supernovae were the only extreme phenomenon populating the galaxy beyond our solar system, that would be enough to fill a nightmare. But they are not, because what a supernova leaves behind is, in many ways, even stranger and more extreme than the explosion itself. When the core of a massive star collapses, the resulting object is called a neutron star. It is one of the most exotic objects in the known universe. A neutron star is roughly 1.4 to 2 times the mass of our Sun, compressed into a sphere only about 20 kilometers across. 20 kilometers! You could drive across a neutron star in about 12 minutes if the surface did not immediately vaporize you in ways that require an entirely new vocabulary to describe. The density of a neutron star is incomprehensible by any earthly standard. A single teaspoon of neutron star material, 1 teaspoon, would weigh roughly 10 million tons on Earth. The gravity at the surface of a neutron star is approximately 200 billion times stronger than Earth's surface gravity. If you somehow fell onto a neutron star from a height of 1 meter, you would hit the surface with a velocity of about 2 million kilometers per hour. The impact energy would be roughly equivalent to a nuclear bomb. From 1 meter, neutron stars spin. They spin extraordinarily fast because they inherited the angular momentum of their much larger progenitor star and then compressed it into an object millions of times smaller. The same way a spinning ice skater pulls in their arms to speed up. Some neutron stars, called millisecond pulsars, rotate hundreds of times per second, hundreds. The fastest known pulsar, PSR J1748-2446 AD, rotates at 716 times per second. Its surface is moving at roughly a quarter of the speed of light, and as they spin, many neutron stars emit beams of electromagnetic radiation, radio waves, X-rays, gamma rays, from their magnetic poles. These beams sweep through space like cosmic lighthouse beams. When one of these beams sweeps across Earth, we detect it as a regular pulse of radiation, hence the name pulsars. The regularity of pulsar pulses is so precise that when pulsars were first discovered in 1967 by Jocelyn Bell Burnell and her supervisor Anthony Hewish, the signal was so strikingly regular that the team initially nicknamed the source LGM-1 for Little Green Men, half-jokingly entertaining the possibility that it was an artificial signal. It was not, of course. But the fact that the universe naturally produces objects whose timing is more precise than atomic clocks is extraordinary in its own right. Some neutron stars have magnetic fields so powerful, trillions of times stronger than anything we can produce on Earth, that they are classified as a separate, even more extreme category called magnetars. A magnetar's magnetic field is so intense that if one passed within roughly 1,000 kilometers of Earth, which will never happen, but bear with me, it would disrupt the biochemistry of every living cell on the planet and kill everything, not from heat, not from radiation alone, from the sheer force of the magnetic field interfering with the electron configurations of atoms in biological molecules. There are currently about 30 known magnetars in our galaxy. They are among the most energetic and violent objects in the known universe, and occasionally they erupt. In April of 2020, a magnetar in our own Milky Way, designated SGR 1935+2154, sitting about 30,000 light-years from Earth, produced a burst of radio waves that was detected by multiple telescopes simultaneously. This was an enormous discovery, because the signal matched the signature of a phenomenon called a fast radio burst, a mysterious, extraordinarily energetic pulse of radio waves that lasts only milliseconds but briefly outshines entire galaxies in radio frequencies. Fast radio bursts had been observed coming from other galaxies for over a decade, but their origin was unknown. This nearby magnetar burst finally gave scientists a direct confirmed source and strong evidence that at least some fast radio bursts are produced by magnetars. But here is what makes fast radio bursts truly haunting. Some of them repeat. Not all, many appear to be one-time events, but some burst sources have been observed firing multiple times, sometimes with apparent regularity. The most studied repeating source, FRB 192112, has been detected hundreds of times. Some bursts come in clusters, some follow patterns. The regularity of some repeating bursts has even led a small number of scientists, a minority, and most researchers are skeptical, to briefly consider whether some of them could be artificial, whether something, somewhere, might be generating them intentionally. The mainstream scientific consensus is firmly that fast radio bursts are natural phenomena, most likely magnetar flares, possibly with contributions from other extreme objects. But the fact that the universe is capable of producing phenomena so energetic and so strange that they briefly make scientists double-check their instruments and ask whether something intelligent made them, that says something profound about the nature of the cosmos we live in. We are surrounded on every side by phenomena that dwarf anything in human experience. Explosions that outshine galaxies, spinning objects whose surfaces move at a fraction of the speed of light, magnetic fields that could unravel the chemistry of life, pulses of energy that cross billions of light-years in milliseconds and arrive at our radio telescopes as whispers from the violent heart of the universe. And through it all, through every supernova, every magnetar flare, every cosmic ray bombardment, every fast radio burst, our small blue world has persisted. Life has persisted. For nearly 4 billion years, In the face of cosmic violence on scales that boggle the mind, something on this fragile planet has kept going, has kept breathing and swimming and growing, and eventually looking up at the sky and asking, what is all of this? That resilience, that stubborn, improbable persistence of life in a universe that seems designed to end it, that is one of the most profound mysteries in all of science. And it is a mystery that gets even deeper when you start to consider what lies at the very center of our galaxy. Because the Milky Way has a heart, and that heart is dark, and it is hungry. We have traveled a long way together. Think about how far we have come. We started just beyond Mars, a planet we have been dreaming of visiting for decades, and we crossed the Asteroid Belt, survived the radiation belts of Jupiter, marveled at the geysers of Enceladus, wandered through the frozen graveyard of the Kuiper Belt, stood at the edge of the Oort cloud, felt the invisible pressure of cosmic rays passing through our bodies, and watched stars explode with enough energy to outshine entire galaxies. We have seen neutron stars spinning hundreds of times per second, magnetars with magnetic fields that could unravel the chemistry of life, and fast radio bursts so energetic and so strange that they made scientists briefly wonder if something intelligent made them. And now we arrive at the final destination of this journey, the deepest, darkest, most extreme place we will visit today. The place that puts everything else in perspective, the center of our galaxy. Right now, as you watch this, you are moving. You probably do not feel it. You are sitting still, maybe on a couch, maybe at a desk, but you are hurtling through space at speeds that would make the fastest jet on Earth look stationary. Earth is orbiting the Sun at roughly 107,000 kilometers per hour. The Sun, carrying the entire solar system with it, is orbiting the center of the Milky Way galaxy at roughly 828,000 kilometers per hour. 828,000. Every single second, you personally travel roughly 230 kilometers around the galactic center without feeling a thing. One full orbit of the galaxy, called a galactic year or a cosmic year, takes our solar system approximately 225 to 250 million years to complete. The last time we were in this exact position in the galaxy, dinosaurs had not yet appeared on Earth. Trilobites were just beginning to vanish. We are not sitting still in the universe. We are passengers on a star, orbiting the heart of a galaxy, and that heart is one of the most extreme objects in the known universe. At the very center of the Milky Way, roughly 26,000 light-years from Earth, sits something that no human eye has ever seen directly, and yet whose existence is now beyond scientific doubt: a supermassive black hole. Its name is Sagittarius A star, written as Sagittarius A with an asterisk, pronounced Sagittarius A star, and it contains the mass of approximately 4 million suns compressed into a region of space smaller than the distance from the Sun to Mercury's orbit, 4 million solar masses. In a space that our inner solar system could swallow, the concept of a black hole is one that most people have heard of, but whose true nature very few have genuinely sat with. So let's do that now. Let's really sit with it. A black hole is a region of space where gravity is so intense that nothing, not matter, not light, not any signal of any kind, can escape once it crosses a boundary called the event horizon. This is not a surface you can see or touch. It is not a wall or a membrane. It is simply the point of no return. The distance from the center at which the escape velocity, the speed you would need to travel to break free of the gravitational pull, exceeds the speed of light. And since nothing in the universe can travel faster than light, anything that crosses the event horizon is gone. Forever, cut off from the rest of the universe as completely as if it had never existed. Sagittarius A star's event horizon, its point of no return, has a radius of roughly 12 million kilometers. That sounds large, and in human terms it is enormous. But compared to the scale of the galaxy, it is a pinprick. a single point of darkness at the center of a spiral of hundreds of billions of stars. For decades, astronomers could not image it directly. They could only infer its existence from the behavior of stars orbiting the galactic center at extraordinary velocities. A team of astronomers led by Reinhard Genzel and Andrea Ghez, who shared the Nobel Prize in Physics in 2020 for this work, spent over 25 years tracking the orbits of individual stars near the galactic center using infrared telescopes that could peer through the thick clouds of gas and dust obscuring that region of the sky. What they found was extraordinary. Stars moving at velocities of up to 30 million kilometers per hour, roughly 3% of the speed of light, on tight orbits around a completely dark, invisible central point. The only object that could account for those orbits was a supermassive black hole of about 4 million solar masses. Then, in May of 2022, the Event Horizon Telescope collaboration, a global network of radio telescopes linked together to function as a single Earth-sized instrument, released the first direct image of Sagittarius A star, a glowing, blurry ring of hot gas and radiation surrounding a dark central shadow. It was not a crisp Hollywood-style image. It was noisy, uncertain at the edges, hard-won from petabytes of raw data and months of computational processing, but it was real. It was actual light from the immediate surroundings of a supermassive black hole at the center of our galaxy. One of the most profound images in the history of human science. Now, is Sagittarius A star dangerous to us? At 26,000 light-years away, the direct gravitational influence of the galactic center is negligible at our location. We orbit it, yes, but so does every other star in the galaxy, and the gravitational dynamics at our distance from the center are gentle and stable. The black hole itself is not about to reach out and swallow us. But the galactic center is not just a black hole sitting quietly in the dark. It is one of the most violent, active, and energetic regions in the entire galaxy. The density of stars near the galactic center is thousands of times higher than in our neighborhood. Stellar collisions, near misses, gravitational interactions that fling stars onto new trajectories, all of these happen far more frequently near the center. Supernovae are more common there, radiation levels are higher, the environment is harsher, more chaotic, more extreme in every measurable way, and occasionally Sagittarius A star feeds when matter, gas, dust, or the shredded remnants of a star falls toward the black hole. It does not fall in cleanly and quietly. It forms a swirling disk of superheated material called an accretion disk, and as the material spirals inward, it heats up to millions of degrees, radiating enormous amounts of energy across the electromagnetic spectrum. Some of this energy gets channeled into jets, narrow, focused beams of plasma and radiation, fired outward from the poles of the black hole at close to the speed of light. These jets can extend for thousands of light-years in either direction, blasting through the surrounding gas and dust and radiating intensely at every wavelength from radio waves to gamma rays. We have evidence that Sagittarius A star was significantly more active in the relatively recent past. Enormous structures called the Fermi bubbles, two giant lobes of high-energy gas extending roughly 25,000 light-years above and below the plane of the Milky Way, were discovered by the Fermi Gamma Ray Space Telescope in 2010. Scientists believe these bubbles were inflated by a period of intense activity from Sagittarius A star somewhere between 2 million and 8 million years ago, a feeding frenzy that blasted material outward at enormous energy. And 2 million years ago, that is recent enough that our earliest human ancestors were walking the African savanna. We live in a galaxy with an active, if currently quiet, supermassive black hole at its center, a black hole that has, in the geologically recent past, unleashed enough energy to reshape the structure of the galaxy itself. And yet here we are, here you are, watching this video, breathing this air, made of atoms forged in the hearts of stars that lived and died before our sun was born. Because here is the thing that all of this, every terrifying, humbling, overwhelming fact in this entire journey has been building toward. Here is the part that I want you to carry with you when you close this video and go back to your day. The universe is violent. It is extreme. It is indifferent to our existence in a way that can feel crushing when you stare at it directly. Supernovae, magnetars, cosmic rays, black holes, radiation belts, interstellar emptiness, none of it was designed with us in mind. None of it cares whether we thrive or vanish. The cosmos does not play favorites. It does not protect the small and the fragile out of affection. And yet, in the middle of all of that violence and indifference and incomprehensible scale, something happened on a small, rocky, water-covered world orbiting an unremarkable star in the outer arm of a spiral galaxy. Something that, as far as we currently know, has happened nowhere else in the observable universe. Life appeared, and then that life, after billions of years of struggling and evolving and dying and adapting, developed the ability to look up at the sky and understand what it was seeing, to measure the distance to stars, to detect gravitational waves from black hole mergers 1 billion light-years away, to build instruments sensitive enough to taste the ocean spray of a moon around Saturn, to take a photograph of a shadow cast by a black hole 26,000 light-years away. You are a collection of atoms, carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus, forged in the nuclear furnaces of stars that lived and died billions of years before Earth existed. The iron in your blood was made in a supernova explosion. The calcium in your bones was synthesized inside a red giant. The oxygen you are breathing right now was produced by stars that are long gone, scattered into space by their deaths, gathered by gravity into a new generation of stars and planets, and eventually breathed in by you right now, in this moment. You are not separate from the cosmos. You are not a small, fragile thing looking up at something vast and alien. You are the cosmos looking at itself. You are the universe becoming aware of its own existence. Every question you have ever asked about the stars, every moment of wonder you have felt looking up at a clear night sky, that is the universe wondering about itself through you. Carl Sagan said it beautifully, and it bears repeating. We are a way for the cosmos to know itself. The space beyond Mars is worse than you think. It is radiation and vacuum and silence and cold and violence on scales that have no human parallel. It is exploding stars and spinning neutron stars and black holes and cosmic rays and distances so vast that our fastest spacecraft would need tens of thousands of years to cross them. It is humbling in a way that nothing else in human experience can quite match, but it is also ours. It is the universe we live in, the story we are part of, and the fact that we can understand it even partially, even imperfectly, even with all the gaps and uncertainties and competing theories. The fact that we can look at a smudge of radio telescope data and say, that is the shadow of a black hole 4 million times the mass of our sun. That is not nothing. That is everything. Keep asking questions. Keep looking up. Keep following the science wherever it leads, even when it leads somewhere that makes you feel small, because feeling small in front of something magnificent is not weakness. It is the beginning of wisdom. The universe is enormous and ancient and violent and strange, and we are in it, and we are paying attention. That matters more than you know. Thank you for taking this journey with me. If this video gave you even one moment of genuine wonder, 1 second where the scale of it all hit you differently, please share it with someone who needs to look up at the sky tonight. Subscribe if you have not already, leave a like, and drop a comment below telling me which part of this journey hit you the hardest. Was it the radiation belts of Jupiter, the geysers of Enceladus, the spinning neutron stars, Betelgeuse, the black hole at the center of our galaxy? I read every single comment, and I will see you in the next one.